All right, like I alluded to at the end of the last one, we're going to talk about dielectrics this time. Let's start off by defining it. So dielectric is the insulator between the plates of a capacitor. And what are they used to do? They're used to increase capacitance. So the normal limitation of a capacitor is if you put too much charge on one side and, well, too much charges between the sides, what can happen is the charges start to jump across. So it's the amount of charge it can hold on to before it starts jumping. Now, if you put something in there that's going to resist it, you can get an even higher electric field in between them before charges start to jump across and complete the circuit. Cool. So when we add dielectrics into our capacitance equation, here's what we had before. What we get is K, where K is our dielectric constant. K equals 1 for vacuums. No, it's VACUUM. There we go. Vacuum is such a weird word. All right, so it's 1 for a vacuum. So the higher K value we get, the higher electric field that we can have between them. So let's look over here. If a capacitor with air normally, so air is nearly 1. It's like 1.00, whatever it is. Air is similar to a vacuum, just like with anything else we do in here. Vacuum and air are going to be very similar because air is mostly empty space. So if a capacitor with air, as its dielectric, has the air replaced with a stronger dielectric, what is going to happen to Q, V, and C? Well, let's write our two equations that we know for capacitance. Here's our normal capacitance one we just got over there. K epsilon naught A over D, and C equals Q over V. So let's take a look and see what happens. So if I increase my K value, what happens to C? These all stay constant. That means C has to go up. So capacitance increases. Well, as a result of that, what's going to happen over here? Well, our voltage just depends on what's supplying the voltage. We haven't done anything to change the battery or the power supply when we put a dielectric in the middle. So voltage is constant. But if that's true, if this one increases, that one stays constant, that tells us our charge increases. Which makes sense because remember, capacitance is how much charge you can store per amount of voltage. So if you can store more charge per voltage, then if your potential difference stays the same, your capacitance goes up, that means the amount of charge you can store is going to have to increase as well. Finally, let's try applying this. I want to find out what is the capacitance of this bad boy right here. Now, paraffin wax, and for any K value you're going to get, you're not supposed to know it. This is just a physical constant. So if you look on Schoology, there should be a link to click on that has dielectric constants. We'll just use those. I'll go ahead and give it to you for this problem. The dielectric value for paraffin wax, so K PW, is 2.2. That means it's 2.2 times as good as an insulator as an empty vacuum. So let's go ahead and solve for it here. C equals K epsilon naught A over D. Let's solve this. So we have 2.2. Epsilon naught is 8.85 times 10 to the minus 12. This is a perfect square, so we'll just take the side length of 6.6 centimeters and we'll square it. That'll give us our area. And then we'll divide by the separation, which is 8 millimeters. So we need to move the decimal point 3 times. When we plug all that in, hopefully that's not off the edge of the page, I get 4.71 times 10 to the minus 11, or 47.1 picofarads. And that's going to do it for our unit on dielectrics.